All right, so good evening, everyone. Welcome to the 934th monthly meeting of the Amateur Telescope Makers of Boston. We are one of the oldest and largest astronomy clubs in the country. And Chris will give you a rundown on how many members we have. It's pretty impressive. Tonight's guest speaker is Lowell Putnam from the Lowell Observatory, and he'll be talking about the Naval Precision Optical Interferometer that's installed there. Okay, I thought it was pretty funny.
Yeah.
All right. Well, Glenn,
Hey,
go
is
ahead.
it going to be as big as the moon?
Well, you know, that's funny. I haven't heard that this year at all. Since 2003, every time Mars hits an opposition, that's what you hear, this internet rumor that Mars is going to appear as large as the full moon in the sky. But I've not heard it this year. Maybe it's past. Maybe there are too many other things that are being distracted. We're being distracted.
It was around last month.
Oh, it was. Okay. Well, hopefully everybody clarified that when they heard it. Set everybody straight.
Isn't there an asteroid for a close approach coming up like the day before the election?
Probably.
Because I think that would apply more to this, you know.
Spaceweather.com lists all that sort of stuff. And there's a whole website for near Earth objects. You can go on and check it out. Well, perhaps, yes. Anyway, Glenn, are you with us? Can you unmute yourself and give us
Can you hear me?
I can hear you.
Okay, well, our astronomy saying for the month, the universe is like a safe to which there is a combination, but the combination is locked up in the safe, which means that professional astronomers are cosmic safe crackers. We'll go on to the next slide. What's going on between now and the next meeting? Well, of course, the big one, Rich mentioned, on October 13th, Mars is going to be at opposition. On Wednesday, the 21st, in the early morning, that was after midnight, there'll be the Orion meteor shower. This is kind of a minor shower. It's you might see about 20 meteors at max an hour. But again, if you're up, it's just worth sometimes going outside. If you can't sleep or whatever, just go outside and spend 5-10 minutes, just see if you see any meteors at all. Sometimes it's just nice to say, well, I've caught a couple of that meteor shower, so I can try for another one. On October 22nd, for you naked eye folks, a near first quarter moon will form a neat naked eye triangle with Jupiter and Saturn looking the south-southwest. And if you're like me, you'll have to get to a good open area in the south. I've got a lot of pine trees in my backyard, and Jupiter and Saturn are really behind those trees a lot of the time. On Friday, October 23rd, 9:30 p.m. Eastern Daylight Time, plus or minus 2 hours, the Lunar X and the Lunar V are going to be visible, and that's a great opportunity to check those out. They'll be just on the dark side of the terminator, and the Lunar X is approximately in the middle of the lunar disk, if I recall, or a third of the way up, but it's striking once you see it. On the 31st, Uranus is going to be at opposition. It'll be in kind of a barren part of the sky in the lower part, the southern part of Aries, and just a little bit ahead of, top of the group of stars that forms the head of Cetus the Whale. Sunday, November 1st, time for amateur astronomers to rejoice. Daylight saving time ends, and we can get out even an hour earlier than we have been lately. I just happened to go out tonight at about 7:30, so now that'll be 6:30. You'll be able to go out literally right after supper time. So it says daylight saving time ends. That means that standard time will begin. And that's at Sunday, November 1st. We usually set our clocks back an hour Saturday night before we go to bed. And on the 10th, Mercury will be at the greatest western or morning elongation. It'll be joining Venus in the morning sky. And this is a favorable one for those of us here in the Northern Hemisphere. Next slide. Rich was talking about this month's Observers Challenge, and it's a pair of galaxies in Pegasus. And most of us, when we think of galaxies in Pegasus, we think of NGC 7331, which shows in the finder chart over there at the left. But if you go about 12-13 degrees directly south near the stars Mu and Lambda Pegasus, you'll find a couple of a pair of galaxies, 7332 and 7339, and their location is shown on that chart to the right. And what I did to find them was I just centered my finder scope on Mu and Lambda, and then got those in a low power field and just kind of moved my scope about 2 degrees toward the west. And there was a pair of 7th magnitude stars, kind of north-south orientation, a little more than a degree apart. And the galaxies were located right between those two. Next slide. And we got pictures from Mario and Doug Paul. And the galaxy on the left is 7339, and the one on the right, the brighter one of the two, is 7332. And we'll go to the next slide. And this is a sketch I made. It's kind of hard to see here, but what I wanted to mention was this William Herschel, when he cataloged these, he gave them both class 2 status, and class 2 for Herschel was faint nebulous objects. Class 1 was bright nebulous objects, class 2 was faint, and class 3 was really faint. And I kind of question him having 7332 as in that class faint, because I was able to see that very easily with a 4.5-inch reflecting telescope. As Rich said, that's much brighter. That's the one you pick up first. 7339, I had to wait a while. I had to let my guys dark adapt. And again, it was basically averted vision. This is with a 10-inch scope, and I observed from about magnitude 5 skies, but it was visible. They're both edge on. It's kind of a neat sight. Next. Okay, I'm going to bring this up. This is a little bit of a spiel, and Rich was kind of to market. I've been trying to get you folks interested in variable stars, and I know sometimes it's like taking a horse to water and getting it to drink. But variable stars are just fascinating. I've given talks about them all over the place, and I want to talk about SS Cygni, and I've already put this on the website, a little bit of a challenge for both the astro imagers and for the visual observers as well. But SS Cygni is it's a cataclysmic variable star. It's a dwarf nova. It's a pair of stars. And if I recall, one is a star pretty much like the sun. The other is a white dwarf. And they're in a binary system very tight. And the white dwarf just sucks material off that star, the major star, until it becomes unstable and it has a stellar belch, if you will. And at minimum, and most of the time, SS Cygni is about 12th magnitude, but every now and then, about every 50 days, without warning, it just shoots right up to 8th magnitude. These outbursts are very dramatic and very sudden. And it's a fascinating star to follow. So I did send out a couple of charts recently just to get some of you folks interested. And we'll go to the next slide. And first of all, this is the view through a fibroscope. There's Rho Cygni. Oh, can we flip back just for a second, Rich? Yeah, when you start out, it's just out of the edge of the field there. I think it got cropped a little bit, but over on the right-hand side, I believe it's Delta Cygni. And if you're looking at Cygnus with a naked eye, look for Delta, go across to Deneb, and then go about an equal distance beyond. You'll see 75 Cygni. That's the star that you want to try to set your finder scope on to locate that. So we'll go from there. And now this is the finder scope. 75, there's Rho Cygni, and from Rho Cygni, you follow its trail of stars down to 75, which is at the bottom there, magnitude 5.1. In my finder scope, Rho Cygni and the stars just above it and below it there, it looks kind of like Antares, or say Altair. It's a 3-star group. So once you found Rho Cygni in the finder scope, just star hop your way down to 75 Cygni. Now over on the right, there's a kind of low power view, and 75 Cygni, it's a kind of a yellow-orange K-type star. It's fairly bright, and it's part of a group of stars that almost looks like the Hyades to me. It sure forms a V-shaped group, and it opens up and you fall and get to a nice little triangle of stars, 8th and 9th, almost 10th magnitude stars. That's the fun. That's where you really begin to find where SS Cygni is going to be. That's the base area, if you will. Next slide. Now here's a picture Mario took, and the star circled is SS Cygni. And just a little bit to the left of it, well, first of all, Mario picked up a couple of galaxies. This, I believe, is with his 32-inch scope. Now, the triangle, what he has is the lower 2 stars of the triangle. The top star is just out of view at the top. But that brightest star in the image there near those galaxies, that's the 8.6 magnitude field star. And if you go to SS Cygni and then go an equal distance beyond and a little bit below, that's the 9.6 magnitude field star. And I know there's a ton of stars here. When I first looked at this, in fact, I couldn't locate the field because there's just so many stars, but basically he's concentrated on the field. And I would imagine if this picture has been cropped, if he would just go a little bit north, the top of there, move that up, he'd probably catch that 3rd star in the triangle. One thing I do want to point out, and you see it there in that little inset there, there's a triangle, and you can see the parts that Mario had caught. And I got to tell you, some of those stars have to be around 20th magnitude. Now, Mario kind of jokingly said, I didn't mention that trio of clusters right there, the trio of those galaxies, rather. And I'm not embarrassed about that at all. What I am embarrassed about, if you look at SS Cygni just below it, there is a beautiful double-double, and I didn't mention that, and I'm totally ashamed and embarrassed. But from what Rich tells me, those stars are all about 13th, 14th, 15th magnitude. The galaxies are probably 15th as well. And I think he caught a couple others. If you go near the top in the left-hand corner, it looks like there's a face-on galaxy right there. Then you have Mario's triplet, and there's a little faint one, so it's actually Mario's quadruplet. And I believe a little south of SS Cygni, about halfway down there, yeah, there's a nice little galaxy right there, and there's one above right there. So he picked up, this is a Hubble image. This is a Hubble deep space image from Mario. So we thank him. And you know,
I don't know if you got the 3-minute one up or the 30-second one up, but there are many galaxies there. I plan on doing a 1-hour exposure of New Moon and really show you some galaxies. By the way, just to help you out, the field of view here is 14 by 23 arc minutes.
yeah, Mario, were you able, is that cropped at the top? Like if that were, could you be able to reveal that third star in the triangle if you were to recrop that sometime?
Well, I didn't crop it. That's my actual field.
Oh,
I have
okay.
to offset it. I just put, so you could easily find it. I put SS Cygni dead center.
Right. And by the way, while we're on this picture, I did mention a kind of an informal challenge to those of you who are astro imagers. This is something different, just a change of pace. And I used to have a book that had images of these cataclysmic variables in 2 stages. One when they were at their quiescent stage, we call it, or they were low. And then a picture right beside it of them during outbursts. And it's dramatic, the difference. And I, again, challenged everybody, the astro imagers, to get an image of SS Cygni when it's near quiescence. And I just checked it out about an hour ago before getting on here. And it's still about 11.5. So it's down right now. It's in a down state. The outburst could happen at any time, most likely late October, sometime to mid-November. But I'm going to show you in a couple of slides. That could be right off the boards. We have no idea really knowing what's going to happen. But Mario's got out of the gates first. For the rest of you astro imagers, give it a chance just while it's still in its quiescent stage. And you don't need a 32-inch telescope. The stars that I look at, generally, SS Cygni is probably 12th magnitude at its faintest. So if you have a 6-inch scope and you want to do some imaging with that, you'll still get that very nicely. That triangle is probably about 10 arc minutes across. And maybe Mario will get a deep sky field of what's inside that triangle of stars. All right, next slide. These are light curves of SS Cygni. Every dot there is somebody's observation. And you can see a couple, the color doesn't show as well, but over on the right-hand side, you might see some that look like there's an X. Those are observations that I've made in the past. They're highlighted. But the top one shows the light curve of SS Cygni for the past about 100 days, starting sometime in early July. And you can see that it had an outburst in early July, and then again sometime about early August. And here's the thing, there is usually when it has an outburst and when it returns to normal, or if it's this faint stage, it'll stay that way for a couple of weeks. But if you look around the middle of the chart there, it got down in its outburst, it got down to about 11.5 magnitude, and then it shot right back up again. And then when it went down, it floundered around for a good period of time there, sometimes between 10.5 and 11.5 magnitude. That's very unusual for that star. It typically sits pretty quiet at 12th magnitude. So it was bouncing around a lot. Recently, it had another outburst, and it's down a downstage. The last couple of observations there, again, they look like crosshairs. Those are observations I've made recently. I had it 11.5 earlier tonight, so we don't know. It could do what it did way back in early August and have another outburst, or it could wait a while. So I really encourage you to get outside and take a look. But here's another thing I found interesting. I went to the AAVSO website, and I had it put out together a light curve for the last 1,000 days, which is about 3 years. And you can see that cycle back and forth between 8th, about roughly at when it's at maximum. And if you look over on the left around early 2018, its base point was about 12.5. And what I found interesting, I don't know if this is a pattern, but if you follow along, it seems like its quiescent period seems to be getting a little bit brighter. Now, I don't know what's going to happen in the future. And if you look at the maxima, they do seem to be getting lower. In other words, the amplitude in those last couple of years seems to have lessened. I don't know if that's a pattern, but that's why this star is so fascinating to follow. So I'm going to just throw one more thing in here for you visual observers. I'd like to see who can be the first to catch the next outburst of SS Cygni. And what you want to do is go outside next clear night, tomorrow night, for instance, find SS Cygni, and it might take you 5-10 minutes the first time around. But this is a star you look at every clear night. So if you go out the second night, it might take you half that much time. And usually within a few nights, you've got it memorized. You can find that star almost instantly and just check it out. And again, I sent the field star as far as the comparison stars. Try to make your own estimates, but see if you can catch it when it shoots up. I'd say around 10th magnitude. Again, it's been acting erratically, but if you just send me a little note saying you've seen SS Cygni, it looks like it's past 10th magnitude. And if we find out that that was the beginning of an outburst, we'll give you an unofficial, you'll become famous in ATMoB journals as far as being a great observer to check this thing out. So again, visual observers, and I'll close things up here. Visual observers, we'd like to see who's the first to catch the next outburst of that, take an image of it. And for rather imagers, and for visual observers, see who'll be the first to actually spot it on the way up. And that's about all I have. If there are any questions, comments.
Thanks, Glenn.
All right, everybody keep looking up.
That's the idea. And again, that's the impetus behind my 19 plus objects that I've been sending out every month now since I think April. And I'll continue to do that through March. And then you'll have a whole year's worth of these really neat objects to look at in the sky. And Glenn will tell us what's coming up each month. And my 19 objects make for great observing lists. So yes, please get out there and observe, everybody. Get out there and observe. All right, Glenn, thank you very much. Tonight's speaker is Lowell Putnam, and he's going to talk about the Naval Precision Optical Interferometer at the Lowell Observatory complex in Flagstaff, Arizona. You know, I was looking at Mars the other night, and with plenty of time to think about what I was actually seeing, my thoughts turned to Lowell's great grand uncle, Percival Lowell, who at the turn of the 20th century was sitting in an observatory in what had to be the most unbelievable wilderness environment. I don't know what Flagstaff was like 125 years ago, but I have to imagine it was really like wilderness, and it was probably cold and really dark, but my thoughts turned to him. And I wonder if Percival Lowell could have even imagined how far we would have come to this day with our exploration of Mars, with the possibility of human exploration of Mars just on the horizon. And so the observatory has grown from its not so humble beginnings. That Clark refractor is Lowell, you'll correct me, but I think it's a 24-inch refractor, right? That's a big telescope out there. And but currently that facility is, I think it was recently refurbished. There is the Discovery Channel telescope and also the Naval Optical Precision Interferometer. And so without further ado, I'm gonna let Lowell share his screen with us. Please give a virtual round of applause to Lowell Putnam. Take it away, Lowell.
We're all muted.
I know everybody's muted.
All right. Well, thank you very much, Rich, and welcome everybody. Glad to be back talking with you. I wish I'd been able to do it in person, and hopefully at some future point we'll all get together again as well. Yeah, that Clark is an impressive instrument. It was when Percival installed it out there, the 5th largest telescope in the United States. It was an excellent instrument for its time. When we refurbished it, they measured the lenses, and they were still within 1/1000th of an inch of perfect, which, considering the age of that instrument and the glass technology at the time, is pretty impressive. That was Clark did as well as he ever could have on that. Tonight we're going to talk a little bit about optical interferometry and what we're doing about it at the observatory. Before I get too carried away here, I do want to make a clear statement, which is that why is my mouse not advancing? Let's do this. There we are. That'll work. Most of what was done here that I'm showing you, I shamelessly stole from Dr. Gerard Van Bell of the observatory. He is the NPOI chief scientist, and he is acknowledged as one of the very top people in the world in optical interferometry. I also want to be very clear, I am not a scientist or an engineer, so I will do my best to explain, but if you push me too far, I do have some limits and I will punt. However, if I get an email or something afterwards with questions, I'll make sure to get Gerard on the hook to see if he can come up with the answers instead of me. So there. Talking about the founding of the observatory and the duty as laid out in the trust to continue the study of astronomy is what Percival laid out. And as we talked about the Clark, that was a substantial investment to make in putting forward an excellent instrument through which research could be done. And that has been the policy and mission of the observatory since its founding, continuing to this very day, to provide the best equipment possible to our researchers and to allow them to have sustained long-term access, which has allowed not only career-long research done by individuals, but actually multi-generational research done by successive scientists studying the same kind of objects or areas, fields of study. As we mentioned, the 24-inch Clark was installed in 1897 out there. It is still in use today for public viewing. If you go out to Flagstaff, and we have actually been able to reopen it, as I was talking a little bit before. So you can actually sign up to go up and see the Clark, and you can do that through our website. The 61-inch Perkins was brought over from Ohio Wesleyan in 1960. In 1995, we built for the Navy the Naval Precision Optical Interferometer, the NPOI, which we're going to talk about this evening. And a new name, it is no longer the Discovery Channel Telescope. By agreement with Discovery, it is now called the Lowell Discovery Telescope. And that came online in 2013. So in terms of talking about interferometry, the value has been established that it would be a good and useful thing to do since Fizeau's work in the 1850s, which was based on the acceptance or the belief, because they haven't been able to quite prove it out yet, on Huygens' light as a wave phenomena in theory from the 1690s. So interferometry as an understood way to do science has been around for some time. That said, Jodie Foster and Matthew McConaughey to the contrary, it's been a bit of a fight to get it to do all the work that we want to do. There was some work in the 1920s on Mount Wilson, which you see in the picture on the right rather. And there was some work with radio interferometry that actually didn't start until the 1940s. Radio interferometry has been doing more work than optical because the wavelengths are much longer, and so the tolerances are easier. So that's why you've seen the big radio telescopes for some time. But optical really had to wait until the mid-90s for the technologies to truly get going, get underway. And why do we care about interferometry? It is kind of a silver bullet science. This is October, so I got to have this image put in here. It's not something that everybody does. Interferometers don't make pretty pictures, and they aren't particularly sensitive. We'll talk about that in a bit. But there are some things they are very good at. And so if you have a werewolf, you do want a silver bullet. And so this is a good analogy. They are very expensive to put together and to manage and keep running. But the results are quite quite impressive. The level of accuracy is something that single telescope operators would not even be able to comprehend with just one instrument. So here's a brief primer on how you get to interferometry fairly quickly. What you see here is a standard Ritchey-Chrétien telescope mirror arrangement, and it's a good and useful one to point out because, as you can see, the light is coming in, hitting the primary mirror, bouncing back up to the secondary mirror, and then down to the focal point. And every path follows the same path length all the way in. And therefore, that's how you get a nice, lovely picture. Unfortunately, that means your primary mirror becomes the limiting size of what you can do. And that has always been the case, is how big can you make the mirror, and how do you go forward from there? So if you break the primary mirror up into some smaller mirrors that are precisely aligned, then you can now make your primary mirror a little bit bigger. And that's an example you see there at the Keck, at the European Extremely Large Telescope, TMT, and the others. So that's the technique that they're following. So if you can break it up like that, what happens if you go to smaller mirrors, but you can now move them further apart? You can now get a virtual diameter that's extremely large. And that is how you get a long baseline interferometer. Again, what you trade off here is that you're losing the amount of light you're collecting in the course of doing this. And you have to make sure everything stays precisely aligned. Otherwise, you don't get the resolution you want. So if you make separate telescopes and then figure out how to bring their light together, and we're going to use in these next couple of figures just 2 telescopes, but you can imagine if you did it with 3, 4, 5, 6 telescopes, it gets more complex, but the principles remain the same. So here you have to still be precise in terms of bringing the same path length. And that's where life can get kind of interesting if you have static telescopes. So if you, instead of doing static lengths, as shown here in the figure, you can do it with delay lines, where you can let light from one telescope play catch up to light received from another. That is important if you're trying to build a large, long baseline, i.e. maximum diameter of resolution. It's also important because if you want to maintain the path length, your accuracy changes. So here we have an example of our 2 telescopes, and they're fine when they're looking straight out at the object that is, so to speak, right straight in front of them. But as the Earth rotates, notice that the path length to the first telescope is shorter than the path length to the second telescope. And you may think that that's kind of crazy, but we actually do need to get to within the same wavelength of light. And that's why optical interferometry has been taking longer and harder to get functional as compared to radio interferometry. So having the delay lines means that you can adjust for this even slight difference in the path length and control it. And therefore, you can now observe a much wider range of the sky. Now, when we talk about resolution and seeing, most single telescopes talk about measuring in some level of plus or minus around 1 arcsecond is like really good viewing, really good seeing for a standard telescope. If you go to the Keck, or if you go down onto the Atacama, they can sometimes get down to 0.3 to 0.5 resolution on some good nights, arcsecond resolution. for something like the NPOI with its long baseline, you're talking about milli-arc second resolution. So you're talking hundreds of times better resolution. And so now all these tolerances, all these little things that we've been talking about here to make sure that path link is maintained become even more important. And so why do we care about being able to measure angular resolution down to that level? Well, there's a couple of things that let us, that interferometry lets us do that can't be done with normal telescopes. We can directly measure the angular size of a star, and if we know the distance to the star, we now know its linear size, and if we know the brightness of the star, we can get its temperature, and we can measure those extremely accurately. And that's not something that is quite so common. And so that's one of the areas where interferometry really steps up and allows us to test out observed, well, I guess I would say theoretical estimates of what's been observed through regular telescopes. Now, interferometry is only one aspect of how we do astronomy. And so I think it's important to sort of step aside here and say, well, what are the things you're trying to do? So we have astrometry. So we can now measure and get more accurate star catalogs, distance measurements. Interferometry, which gives us angular sizes. Photometry, spectroscopy, which is where a lot of work is done in modern research astronomy. And then astroseismology. Now, the reason that you see the orange here and then the lighter green is the orange involves a lot of modeling. And down here, the lighter green involves some amount of modeling. So modeling is not quite as absolutely accurate as direct observing. But if you start to see where we get the direct results, you see where interferometry really contributes down to getting linear size, which then if we get good models around density, allows us to know about mass of objects. And we're talking objects, obviously, far, far away. So interferometry fills a very specific niche that allows us some really good science and some really good discovery work to take place. Now, specifically talking about the NPOI, which is what I will be calling it for the rest of the evening. Its original name was the Naval Precision, Naval Prototype Optical Interferometer when it was built back in the mid-90s. Since then, because of some changes in technology and changes in the Navy's decision to not build a real interferometer, they have changed this to the Precision Optical Interferometer. Its major funding came from the oceanographer of the Navy, United States Naval Observatory, and the Office of Naval Research. We also got some of the instrument funding from the National Science Foundation. This is a facility that is a collaboration between the U.S. Naval Observatory, the Naval Research Laboratory, and Lowell Observatory. So we are both a science partner and a contractor to USNO and NRL in running this. This is a picture looking at some of the array lines to give you a slightly better view of how this all plays out. If you were flying overhead at our facility, Anderson Mesa, you would look down and you would be able to see the dome that has the 72-inch Perkins, which is now owned and operated by Boston University, and the 42-inch Hall telescope. But if you were to zoom out a little bit, over here, the Perkins and the Hall at the left, and then you see the array that is the optical interferometer. So this is what makes it the longest baseline optical interferometer in the world. What you see here is the combiner room, which we'll take a look at in a second. And here are the long delay lines, so that if you were collecting light from telescopes out at very far distances out compared to what you're looking at, you can make adjustments quite substantially in terms of that, and then bring it into the more accurate, what are called fast delay lines inside the combiner room. So I'll talk about that in a second. So the current infrastructure on this, we have these 12 centimeter imaging siderostats, and they've been primarily used for astrometric work. We'll talk about that. We have the ability to gather light from 6 different telescopes, typically 2 on each of the 3 legs. The long delay lines are currently offline, but we're working to get them back online. And obviously that does limit what kind of baselines we can use. And while initially the Naval Observatory was particularly interested in improving the accuracy of their star catalogs, that has become less of a priority for them, and more interest in binary stars right now. So in terms of the current performance, this is in the combiner room where the light is finally brought together, bouncing through all of these various mirrors, and then coming up against typically a CCD. This is the original combiner. And one of the things that was a limiting factor on it is that when we talk about the N-way permutations, so you can combine any combination. If you're using 6 telescopes, and call them telescopes 1 through 6, you can take any combination of any 2, which would get you 21, I believe, combinations. Then you can have any combination of any 3, any combination of any 4, any combination of any 5, and of course, 1 combination of all. So the classic combiner didn't have all the capabilities we wanted. And given the current mirror arrangements, the sensitivity is relatively limited. So if you were to go out to the Anderson Mesa and lie on the ground outside the one of the buildings there and look up at the sky, what you can see with your naked eye is about what the NPOI can see. We did get a NSF grant to put in a new combiner called Vision. It collects every permutation, and its spectral resolution, as you can see, pretty good. And again, we're gathering to within 10 nanometers of accuracy. I mean, we're down into the area of quantum effects when we talk about the light combination accuracy that we're doing. And with new cameras, it's been able to get to about 5.3. So this is a little frustrating, and to all of us as research partners. And we've been working on an upgrade, which came from the Naval Research Labs, to add 3 1-meter plane waves to the array. And Gerard, as the PI, got to come up with a name for the project. And as you can see, he does read a little bit too much of Lord of the Rings. So Palantir is the name of the project. And what it's doing is it's getting us large apertures. So 1-meter telescopes, some improvements in the delay lines, and an increase in the collecting area. So we're going to see ourselves go from 5.3, 5.5 to very close to 10. There's some hope we actually may be able to go better than that. Every order of magnitude that we can improve the light collecting for gives us 1,000 times more objects to see in the night sky, approximately, and opens up another area of science research that we can do. So getting up 4.5 magnitudes deeper or fainter is really going to open up the amount of science that the NPOI can do. And this project is we should be at first fringes by the end of the year. So that's a good thing. So what does this look like? Or what do large apertures gain for you? If you set them up right, and we have examples here from Paranal, the upper one, and a slightly old from IATA, and or is that Chera? Actually, I think that picture is Chera. The upper one here is done in Chile. We can move the telescopes around, and we'll talk about that in a second on trailers. And we can get approximately 8-meter baselines or go all the way out to the 432-meter baselines. And we can simply move them around during the day, set them up, and then do observing runs that night. And this technology that we're doing sounds kind of crude, but it's actually very, very effective. And to give you an example, there is one of the standard 16-foot Astrohaven domes on a trailer. It didn't come that way on the interstate highway because it was too wide. So the domes actually had to be assembled on the trailers once they got, they came in their kit form on the trailer and then got put together. And you can see the legs underneath here to help isolate the telescope once it's in sight. It's a little interesting to watch when they put the telescope inside the dome, but obviously it's pretty straightforward, and you hope for a nice sunny day when you're doing it. To give you an example of one of the plane waves, as I said, these are 1-meter plane waves. It was installed, and on the same night that it was installed, it took its first official first light photo. 3-minute exposure, unguided, unfiltered, just a nice shot of M51. Now, to talk about some of the science cases that we would be doing with this, one example is planetary formation. So ALMA, which is a radio telescope, can look at the outer region of a gas giant where planetary formation might be happening, but NPOI can take us all the way into the center. So this is an ALMA image on the right, but the NPOI field of view would actually be able to take us right to the center and watch it. So that's one example of the kind of things that we can do with an optical interferometer. Another example is imaging exoplanet transits. So you can do that with an interferometer because the planet shadow makes a perfect star spot. And you can actually use that to determine atmospheric composition. You do need very high signal to noise ratio, which is where having the larger mirrors makes a huge difference. And this is the theory paper, as Gerard noted here, was published in 2008. We're actually looking to be able to do this as we bring the 1 meters online. So those are 2 examples of the science. So with that, I think got an example here of how Venus looks against the sun. So this is the kind of resolution we could do of planets around other stars. And so we think that's another really interesting piece of science to do. With that, I think I will stop sharing and see if there are any questions that have come up in the chat or anything else people would like to talk about.
Well, Lowell, I'll just mention that one of my favorite things with exoplanet transits is your ability to look at atmospheric composition of those planets. That's amazing. First of all, it's amazing. But secondly, you know, last month we heard about the way we can look for extraterrestrial life. And one of the things that was mentioned was to look for the presence of oxygen in atmosphere. If suddenly the Earth were to lose its ability to regenerate oxygen, it wouldn't take long for oxygen being very reactive to disappear from our atmosphere. Not very long, tens to hundreds of thousands of years. So if you find a planet around a star and you see oxygen in its atmosphere, you have to be, that would really pique everyone's interest, because it either means there's some unique geological process taking place there, or it might be a biosignature that we could sort of investigate more deeply.
And other molecules also show up that way. Witness the recent study that came out about looking at Venus's atmosphere and
Mhm.
some of the potential biomarkers because of some of the molecules that you see there. So yes.
And so in my in one of my extending my thought out, wouldn't it be awesome? You've all seen pictures of the Earth at night. Wouldn't it be awesome if your optical interferometer could image the disk of that planet and see lights of perhaps cities? I know this sounds like the world is sci-fi now,
That
but
may be pushing the technology a little beyond its capability.
it's
but,
only the 21st century. We have plenty of time.
there you go.
But I think as that technology advances, that is not beyond my imagination, that you could do
Well,
that.
There's also again this issue of ground-based observing versus in space observing, and Gerard is actually working on a project to build an interferometer in space, and it's actually one of the first prototypes is getting some testing in Florida right now to prove that we can keep everything aligned properly.
Mhm.
But there again, what it'll end up being is a sort of a balancing act of seeing something in space without the atmosphere distorting, but then still needing ground-based capability to follow up and do some of the more detailed work.
Mhm. I'm amazed that you can move the telescopes and actually get everything, I guess, aligned back
They've
before
been,
nightfall.
well, in this way, and the picture I showed you of from Chile, those are 4-meter telescopes. They move them around almost the same process.
It's
So
crazy to think they could do that and get away with it, you know?
we're talking about moving 1 meters around. It's a little bit more straightforward.
Nice. Mark has a question. Mark, just unmute yourself.
Nope. You're muted, Mark.
Now try it. Can't hear Mark.
And if you type it in the chat, then I can try and answer it.
Sorry, Mark.
Mark, just hit your space bar.
Yeah, try that. Just hold the space bar down. See if you can unmute that way. No.
You have to hold it down while you're talking.
Yes. Oh well, we'll get your audio fixed. Any other who else? There must be other questions. This is pretty cool technology. How many optical interferometers would you say there are in operation today?
Ones that will admit that they exist. So there's Chara out in California. There is the NPOI itself. Magdalena Ridge has been working hard to build one, has not yet gotten that operational. The Air Force has one in Hawaii, but it's only like 2 telescopes, so it's not particularly. The Keck, remember the Keck outriggers and the furor that went up about them was the Keck can use its 2 telescopes as an interferometer, so it's very large, but only 2. And they do work that way. And then, as I said, down at Paranal in Chile, you have, they do 4 meters as outriggers to the one of the 8 meters. So that's pretty good.
And how does the resolution of your interferometer compare with, say, like when the Tech was running interferometers?
So the answer is the resolution can be better. It depends on the object you're looking at and a bunch of other varieties, but basically having the long baseline allows you to do some things that nobody else can do, because simply you create, as it were, a virtual telescope with a 432 meter radius. And that's now you're getting up to something pretty decent size. Okay, Mark came in. I understand why the Navy would have been interested back when you started. What is their interest in it today other than pure science? Okay, so the answer is you've got two different branches of the Navy, and branches, whatever, subsets of the Navy that are interested. So U.S. Naval Observatory, they originally started wanting it in astrometry and more accurate star catalogs. That became less of a priority, but they are still interested in precise measurements of binary stars. I don't ask them too much questions about why, but the U.S. Naval Observatory is is both the timekeeper and the locational accuracy center for the U.S. military. One of the things I know when the star catalog accuracy that they wanted to improve was because if they improve the catalog better, they can make the GPS satellite systems be more precise in their location. And therefore that in turn makes our nice little devices that we're used to wandering around and have ways tell us when to get off the highway become that much better as well. And binary stars, binary stars are very precise in some ways. And so studying them helps them improve some of their, again, precision capabilities. NRL is interested in faint object imaging. And they're also interested in some of the technologies that go into the optical interferometer. So that the remote sensor division inside NRL is sort of partners in there and uses this as almost like a prototyping lab for some of the stuff they're interested in doing.
Lowell, do you think it would be possible? Glenn mentioned the star SS Cygni as an example. I don't know. I was just going to look up quick how far away that star is. I don't know how far away it is, but with your capability to do high resolution stuff, do you think it's possible to examine a star like that system to sort of try to figure out what's going on? You know, Glenn talks about how the light curve has started to misbehave itself.
The answer is right.
Say that again.
So NPOI, when the 1 meters are fully online, it'll go to about 10, somewhere between 10 and 11 magnitude. So you showed the light curve there, and the answer is we would be able to track some of the light curve, but not all of the light curve because it's going down to 12th magnitude, and that's now sort of dropping out as too faint in the object. But we would be able to track it for most of it. And yes, I mean, some of the precision you would get on it would be pretty phenomenal in terms of understanding maybe a little bit more about why it's doing the variability. I did see the Art and Sharon Starbo. Hi guys, out there on the West Coast. Will the creation of the U.S. Space Force change interferometry at NPOI? To be determined is the answer to that. It is not yet clear, and you can imagine the bureaucratic infighting that might be going on, exactly what areas of research, space research, will end up falling over into the new Space Force versus staying in their traditional homes. Will things be taken out of Naval Research Labs or USNO and moved in there? And by the way, if they do they end up getting more money and more capacity to do things? I mean, so the answer is don't know, could be good, could be bad, and not under our control. So other than that, you know, Mrs. Lincoln, the play was fine. So we'll see how it goes in a moment. From Ken.
Ken Lonnie had a question.
Yeah. Plane wave scopes, how's the beam combining done? I don't recall seeing various beam lines at NPOI when I visited a few years ago, but a larger diameter was true. No, they're traveling. They're traveling back in through the same light tubes. So the pads are poured, and there's a connection that you can make so that at each one, when you locate an NPOI, locate one of the 1 meters, it's now using the same tubes as any of the sidereosats or anything else.
I just wanted to jump in for a second. You mentioned the interferometers at Keck and the VLT. The one at Keck has been decommissioned.
Yeah.
The one at VLT still exists, but it's used very rarely. And the reason is pretty obvious. You've got these world-class telescopes, which individually can be looking at two different objects. And it takes one hell of a proposal to get the time allocation committee to agree to like commit time for all the telescopes to be using together. And as you pointed out, it's really hard to do. So that's why I think there's a niche for these dedicated projects like NPOI.
Exactly. And that's one of the things that the observatory has been very strong at is, as I said in the beginning, sustained long-term access to equipment to do the kind of long-term viewing research that you can't do somewhere else. I mean, as you pointed out, to take over a bunch of 4 meters and an 8 meter, yeah, you may get one night, that you get to go do that. But then you're not going to be able to come back there the next night and the next night and the next night and the next night. Whereas the NPOI is something where we have a guaranteed amount of time, and we can come back and in time slot out and observe with the same instrument, looking at the same stars over time, and build up much better database information. John Harrington says, how much impact do local seeing conditions at NPOI affect the facility's resolution? The answer is Anderson Mesa is still pretty decently dark. So seeing there is typically 1 to 1.5 arc seconds is sort of a median point in there on the bell curve. And for NPOI, that's good. That's thoroughly usable. The site conditions don't interfere with this kind of science that we can do there. Obviously, it's darker out at the LDT, where that's sub arc second resolution out there in terms of where the median point is in the bell curve, just below 1. So that's a nicer, darker site. But the thing about NPOI is you need a large amount of space. I mean, you need a large capability, particularly get that long baseline. We're actually talking about doing a proposal to increase the baseline too, at least on 2 of the legs. One of the legs ends at the edge of a cliff, so trying to extend out too much further is going to be more difficult. 2 questions, Monty Brandenburg. How long does it actually take to realign after a reconfiguration? The answer is 24 hours. It's so we finish the night's observing, we move a telescope, align it during the day, bring it back online, and it's back online that night. So that's for the answer to that. With the existing telescopes, we are trying to work. It would be nice to work towards even faster switching, where we could switch around configurations inside the same night. And if we had 3 more 1 meters, we could actually stage them in different places and then do different combinations on the fly. That would be desirable and technically doable. Not an issue. On the siderostats, there appear to be a gas purge fill system. We're actually we pump the it's down to a vacuum. Now it's getting older and some of the things leak a little bit, but it's still pretty much a vacuum all the way through the whole system. When we get too much leakage, then we have to go find out where that is and replace it. But pretty much all the time we're running at a vacuum there.
I think my mic's working now.
There you go.
It is.
Hey, amazing technology. Another quick question. I noticed you have the array for the smaller scopes. They're like in not a V pattern, but I noticed it was a separate pattern. Now those are separate from the larger scopes that you have now, right?
No,
Or are they-
actually, so there are 3 legs of the array, and they are 120 degrees apart. And yeah, think of a peace sign. Okay, and so that's where the combiner lines start. So you can pick any two. You can have 2 takeoffs from every leg, so you can have up to 6 telescopes in combination. The 1 meter telescopes, there are pads that will be poured. Some of them have been or being poured, so that they can put the telescope at any one of the collecting points on any one of the legs. And then they figure out what configuration they want, position them there during the day, and then they're good to go.
So rather than putting those on some sort of a rail system, I don't know whether that's a stability issue where you could literally just keep moving them on a rail.
Yeah.
Maybe.
So how it works with the siderostats is it's simply some tip tilt mirrors, the pop-up mirrors that come in, and you just pick which ones you're already going to take off because they're fixed already on the lines, and you can just pick a combination there. The trouble is they're very small, and to remount larger mirrors in there is a very expensive endeavor. For the amount of times that people want to change the baseline, the combinations, it's really, I mean, if you want to write a large check, we're happy to do it, but being able to simply move around the 1 meters meets so many of the science cases that it's just the most cost-effective way to do it.
Thank you.
Yeah. Phil Levine, do you consider SpaceX and Starlink satellites a significant impediment to research? Oh boy, hand me a softball or a hamburger. Yes. There is no question, even with all the work that they're doing, that they will be an impediment. The only question is how much. There is no way with the array, the satellite arrays, they're talking about putting up these fields of satellites, that it won't interfere. Particularly optical, although there is some threat to radio astronomy as well, because some of the frequencies they're using to downlink are right on the edge of some of the key frequencies used for radio astronomy as well. So, and by the way, SpaceX and Starlink, they're being reasonable. They're trying to make accommodations. There's no regulation. If they went and you went and took over some small nation somewhere and built a spaceport, you can launch whatever you can get away with. There's no regulation on what gets launched and how it's configured and what orbits they get into, other than not wanting to run into somebody else. So, I mean, there was a Russian company that talked about putting up array satellites so they could do billboards in space. They ran out of funding, thank God. And yeah, there is a UN conference going on this week to address this. Jeff Hall, our director, is the American Astronomical Society. He's the chair of the committee that's dealing with this very subject. And boy, put a nickel in Jeff and you'll get somewhere. There is, by the way, a new report out that they just put out about evaluating some of this stuff. But I mean, the answer is yes, it does do it. It will cause impact. The only question is, can you minimize it?
Well, if there are no other questions, then Lowell, thank you very much. Let's give another big round of a virtual round of applause. Woo! Thank you very
all
much.
kindly.
I'm going to,
Anyway.
I'm going to share my screen for one more second because I have my closing slide here. Of course, I'll leave the meeting open for as long as folks want, but the next monthly meeting will be on Thursday, November 12th at 8 o'clock. I'll probably open the doors again at 7:45. And the next ATMoB board meeting is on Thursday, January 7th at 8 o'clock.